All right, good day, everyone. So this story is that we're talking about today is about the principle of linear superposition, which is a story of what happens when I have two disturbances, two waves, and they coexist, right? So one way you can think about it is you can say, suppose I have a wave that is described, the mathematical description of it is y1 of x and t. And all that is saying is that I have some disturbance that has a spread over location and it varies as time goes by. So think of, for example, the surface of the ocean and there's a wave coming in and then you take snapshots and for every snapshot you're looking at a specific point in time, but everything is spread out in position. And then you take another snapshot at a later time and another snapshot at a later time. So that's time passing by. So these are the two variables, the location and the time, and that tells you what the disturbance is. This function here, this mathematical function tells you what the disturbance is at some location at some time if you plug in. So suppose I want to find out what the disturbance is at a specific location and at a specific time. Then the disturbance would be y1 of that particular position and that particular time. Okay? In other words, if this was, for example, describing something like amplitude times the sine function of twice pi times some frequency times time minus twice pi over some wavelength times position, then if I plug in t naught here and I plug in x naught here, that gives me this function, that gives me this value here, the value of the disturbance at that particular time at that particular location. Okay, and now suppose that I don't just have one disturbance, but in fact I have two disturbances that are happening, and the second disturbance, let's say we call it y2, and again it's described as a function of position and time, similar to the other description. And then you say at that particular location, at that particular time, I get y2 of x naught and t naught, right? Now suppose that these two disturbances are happening. So I have y1 and I have y2, and I want to find out what is the overall disturbance. So let's say y1 is coming from some source, right? So a boat is passing by and is generating a wave, and then a different boat is passing by and is generating a different wave, and I want to know what is going to happen at a specific location. So I have a particular buoy and I want to describe the motion of that buoy. Then that means that I want to think about it at that specific location, but as time passes by. Right? So how do I describe that? This is called the superposition of the two waves. So I'll write something like the overall disturbance at that location, at that particular point in time, has to do with the amplitude due to the first source and the amplitude due to the second source. And the principle of superposition tells me that I can add the two amplitudes together to find the overall amplitude. It didn't have to be that way, but it turns out that this is the case. The principle of linear superposition tells me that if you want to find the overall disturbance due to two different sources, what you have to do is you have to add the amplitudes, the amplitude from the first source plus the amplitude from the second source. Now, this will give you some phenomena that are really, really quite interesting because of this idea of the sine function could be positive or negative, right? So if the sine function, this sine function here that describes the wave, this sine function here that is describing the wave could be positive or negative. So this one could be positive or negative, this one could be positive or negative. If they're both positive, so that means I'm going to get a disturbance that is bigger than each of the disturbances. If one of them is positive and the other one's negative, then maybe they cancel each other and I get no disturbance at all, or maybe they're both negative, so I get a bigger disturbance that is in the negative direction, right? So this idea is called the interference, and we'll see a bunch of phenomena that happen when this interference happens. Now, this describes the position and this describes the disturbance of the buoy at a particular position at a particular time. Now, what if I want to sit down and watch the buoy as time goes by? Then I could do something like this. I could say, you know what, I don't want to know a specific time. I just want to sit down and watch it as time goes by. So in this case, this would be the general time, not just the specific time. So here it would be the disturbance at some location, specific location x naught, but in all time t, right? So I'm just sitting there and I'm watching the buoy bounce up and down due to the disturbance that is the sum of the two disturbances, okay? Or I can just take a snapshot of the two waves at a particular specific point in time, but I'm looking over all locations. Then in that case, it would look something like this. I'll get at specific point in time, but for all space, right? So suppose I just take a snapshot, then for all space at a specific point in time, this would be for all space at that particular time, for all space at that particular time, okay? So these two kinds of descriptions of the wave are also valid for the superposition of a bunch of waves. So let's see how that will help us describe all of these interference phenomena. So suppose I have two not complete oscillatory waves or periodic waves, but just two pulses, right? And suppose that at some point in time, this pulse here is described by y1, oops, and this other pulse here is described by y2. And I want to know what will happen when both of these at a later time are going to be at the same position. So now I'm looking at a specific time, and here are all of the positions x. So this was at a specific time, all of the positions, and then this is a little bit later time, all of the positions, and then a little bit later time, all of the positions, right? So I say, what is happening here? First of all, I get y1 as a function of position, and then I get y2 as a function of position. And then what happens a little bit later in time is that they both occupy the same position. But because the two disturbances are positive, they add up to each other. And then a little bit later in time, what was on the right here, this disturbance y2 is now on the left because it's moved past it. And what's on the right is a disturbance that now has moved to the left once it passed this point. So this is the sum of the two disturbances here once they come to the same position. Now, what if one of them was actually a pulse that is in the opposite direction like this? Then I get the pulse on the left is moving towards the right, and the pulse on the right is moving towards the left. And once they occupy the same position, because one of the disturbances is positive and the other one is negative, then they cancel each other out. So at this particular moment in time, for figure B here, at this particular moment in time, the two disturbances are canceling each other, and I get no disturbance at all. So the overall disturbance is 0 here over all positions. And then once they pass each other, I see what was on the right is now on the left, and what was on the left is now on the right. Okay, this is called the principle of linear superposition, which says that when two or more waves are present simultaneously at the same place, the resultant disturbance is the algebraic sum of the disturbances from the individual waves. Or in other words, I'm adding the amplitudes of the disturbances. So you can see, for example, here is the story in which I'm getting two pulses moving towards each other, and you can see successive pictures in time, and you can see the constructive interference happening in front of your face, right? These two wave pulses interfere with one another, so that what's moving from the left and what's moving from the right, they come together, and at that specific location, they add up, and then what was on the left now moves to the right, what was on the right moves to the left. But if these two pulses instead are in opposite directions, then you can see what happens when they come together. They pretty much cancel each other out, right? You can see a point in which they really just cancel each other out. So this here is compared to the previous situation in which they add up. Okay, so this part here is called destructive interference. This kind of phenomenon is called destructive interference. That's what happens when the amplitudes are in opposite directions. So they end up canceling each other. That's called destructive interference. But when the amplitudes add up together, that's called constructive interference.
I've got a demonstration here on a little pond where we can see this with water waves. I have two sources, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there.
So let's look, for example, at something that was just represented by these two sources of water waves. But suppose we're thinking about sound waves. It's a similar kind of story, right? So suppose I have two speakers here producing sound, and this is producing a sound wave that is traveling in this direction, and this other source is producing a sound wave that is traveling in the other direction. And I'm standing here at this location. So I'm picking a specific location and I'm looking at the disturbance as a function of time. If only one source was on, this is the sort of thing that you would see. You would see the disturbance happening as a function of time like this, just from the one source. If only the other source was on, you would see the disturbance happening like this. Now, suppose you're standing at one of those specific locations in which the troughs are meeting with troughs all the time, right? So at the same time, the trough comes with the trough and the crest comes with the crest. So see, the crest is lined up here, the trough is lined up here. So you're standing at one of those special places, in which case what is going to happen is that the two waves are going to add up together, and you're going to hear a wave that has twice the amplitude. Yeah? Because you're standing at a location in which something happens that we call constructive interference. But if you happen to be standing at a different location in which the crest is lined up with a trough and the trough is lined up with a crest, then when you look at the overlap of the two waves, of the two sources, then you get completely destructive interference. And that was represented in the water picture by the points at which the water was not being disturbed at all, even though if I just had one wave, it would be disturbed occasionally. But because the two sources are overlapping, there are specific points there in which you get absolutely no disturbance even as time passes by. So this means then that there are locations where the crests would line up with each other, and there are locations where crests would line up with troughs as time passes by, right? Just as we saw in the water example, there were locations that as time passed by, there was always no wave there, but there were locations where the waves were always adding up, okay, as time passes by. So suppose I'm standing at, I want to know really where these different locations are. I want to know what determines the locations at which things would constructively interfere and what determines the locations at which things would destructively interfere. So I'm trying to find out the condition for these constructive and destructive interference from two different waves. Now, I can tell you exactly what the answer is, but let's walk through it and sort of try to reason about what's the case. So for example, if you look at one of these points, pick any one of the points that have constructive interference. Let's say I'm going to pick this point here. I want to point something out to you. I want to say, think about how far this point is from the first source. Well, if I start from a crest and then a crest and then a crest, so this would be a wavelength, right? From a crest to a crest, that's called a wavelength. And then from a crest to a crest again, that's another wavelength, okay? And then from a crest to a crest again, that's another wavelength. So on this point here, I am 2 wavelengths away from the first source, and I am 3 wavelengths away from the second source. So I'm gonna call this point 2 wavelength and 3 wavelength away. So this here is away from the first source, away from the second source. And then I'm going to look at this point here, and I find myself to be 1 2.5 wavelength away from the first source, 1 2.5 wavelength away from the second source. So I'm going to call this point 2.5 lambda and 2.5 lambda, right? 2.5 wavelength and 2.5 wavelength. And then I look at this point here, and I find that it's 1 2 3 wavelength away from the first source, 1 2 wavelength away from the second source. So this would be 3 lambda and 2 lambda. I'm just trying to find the pattern here, right? I'm trying to sort of lead you to find the pattern. And then at this point, it's 1 2 3 1 2 3. So this would be 3 lambda and 3 lambda. Right. Now let's see. Can I see any pattern here? This is 2 lambda and 3 lambda. The difference between them is -1 lambda. The difference between these two is 0 lambda. Between this one is 1, and between this one is 0. So it looks like the difference could be 0 lambda or 1 lambda. Then I would get constructive interference. Okay, so what about if I think about the destructive interference points? Well, I get 1 2.5, and then I get 1 2 3. So 2.5 and 3. And this one would be 1 2 3 1 2.5. Right. So the difference between the two here is half a lambda. The difference between the two here is half a lambda. While the difference here was 1, the difference here was 0, difference here was 1, difference here was 0, right? So it looks like if I have 0 or 1, then I'm getting constructive. If I have half a lambda, then I'm getting destructive. And in fact, turns out that if I generalize this more, that's exactly what the pattern is. If I have 0 lambda difference, 1 lambda difference, 2 lambda difference, 3, 4, 5 lambda, so any integer multiple of lambda difference between the path length from the first source and from the second source, then that's called constructive interference. But if I have an integer and a half multiple of lambda, then that's called destructive interference. So it looks something like this. If the difference in path lengths is 0 or an integer number of wavelength, that leads to constructive. If the difference in path lengths means the distance that was traveled from the source to the location at which I'm thinking about whether there's constructive or destructive. The distance traveled from the first source to that point versus the distance traveled from the second source to that point. If the difference between these two lengths comes out to 0 or comes out to an integer multiple of wavelength, then I get constructive interference. But if it turns out to be a half a wavelength, 1.5 wavelength, 2.5 wavelength, etc., then I get destructive interference. And we write it like this. We write the condition this way. I say the difference in path length, which this here, the difference in path length, is described as L1 minus L2, which is, this is the path length from the source 1 to the location at which I want to calculate the interference. And this is from source 2 to the location at which I want to calculate the interference. So if I had a point here, this would be L1, and this would be L2. If I had a point here, this would be L1, and this would be L2. See that? So the distance from the point to, from the source to the point at which I want to calculate the interference, minus the distance from the other source to the point at which I want to calculate the interference, that's called the difference in path length. And if that difference in path length compared to the wavelength is an integer multiple or 0, so n is equal to 0, 1, 2, ... then that's called constructive interference. And if the difference in path length compared to the wavelength is n plus a half, where n again could be 0, 1, 2, etc., but now adding a half to it, then that's called destructive interference. Okay, let's see how this plays out in a problem. So here's a question. Suppose I have two loudspeakers A and B, and the word in phase here means that they start out crest at the location of the speaker itself, they're vibrating with the same phase. So if you remember the water video, when he was doing the spheres, he was doing the spheres with the same rhythm. So he started out, they're both high together, they're both low together, they're both high together, they're both low together at their origin, at their source. But then the question is, by the time they get to the point at which I'm calculating the interference, are they still lined up crest with crest, or are they now lined up crest with trough and trough crest? And the way to find that out is by calculating the path difference and comparing it to the wavelength. So suppose I have two in-phase loudspeakers, A and B. So they're starting out together, you know, crest lined up with crest at their particular sources, at their locations. And I know the distance they're separated by, 3.2 meters. And then a listener is stationed here. So this is the point at which I want to find out whether there's going to be some kind of interference. Is it constructive or is it destructive? The listener is stationed at point C, which is 2.4 meters in front of speaker B. And I'm given that this is the right angle here, 90 degrees. Both speakers are playing some particular frequency, 214 hertz frequency tones. And the speed of sound, that's the speed of the wave that is traveling in this direction, is given to me as 343 meters per second. And the question is, does the listener hear a loud sound or no sound? A loud sound, of course, means that there's some sort of constructive interference because the two waves are adding together to add to a loud sound, or no sound, that means destructive interference. So that means the two waves are adding together, but they're out of phase. So the crest is lined up with a trough and the trough is lined up with a crest. So then you get no sound at all. You get zero, that you get destructive interference. So no sound as time passes by. So I want to find out whether, so the question really is about what kind of interference is happening at this point C here due to the two sources A and B. Okay, so the way I think about this is I say, what I really want to find out is I want to find out the ratio of the difference in path length compared to the wavelength of the wave. If this comes out to be 0, 1, 2, 3, 4, 5, then it's constructive interference. If this comes out to be 0.5, 1.5, 2.5, 3.5, then that's completely destructive interference. Okay. If it comes out anywhere between, so let's say it comes out 0.25, then that's some kind of destructive interference. It's not completely destructive interference, but we're not going to worry about that for now. So any problem you're going to see is going to be either give you, an integer or an integer and a half, right? To make sure that you're falling into one of these two categories, completely constructive interference or completely destructive interference. Okay, what is this DL here, delta L? That's the difference in path length. That's the difference in length between this one and this one. The difference in length between the distance the sound has to travel from the first source to the listener versus the distance the sound has to travel from the second source to the listener. So if I call this LA, right, the length from A to C, okay, fine, I'll call it LAC, and this is LBC, then delta L here would be the difference between the two. And I really don't care which one is bigger, so even if it comes out negative, I don't care. I'm just going to look at the difference between the two. Now, obviously, LAC here is bigger than LBC, so this should really come out to be positive. And then I'm going to compare that to the wavelength, and I'm going to see if I get like which condition I get. Now, what is the length LAC? I don't know that, right? But I do know this distance, and this angle. So I really could think of this right angle triangle here, and I can use the Pythagorean theorem to find LAC. And then LBC is already known. So I can figure this out using the Pythagorean. I know LBC, and I need to figure out the wavelength. So first, let's figure out LEC. Okay, so in different problems, you might have to do different things to find this distance, or it might already be given to you. But in this particular problem, we have to find it, and we have to find it from the geometry of the problem. So I say in this case, it would be, because it's the hypotenuse, it would be the square root of this side squared plus this side squared. That would give me the hypotenuse squared. So 3.2 meters all squared plus 2.4 meters all squared under the square root. And that will give you 4 meters. The reason I recognize this one is because this square is a very well-known square, right? It's 4, 3, you know, there's a square that is 3, 4, 5, right? So this is 3 times 0.8, this is 4 times 0.8, so this becomes 5 times 0.8, which is 4 meters. Okay, but if you put it in the calculator, you get it. Okay, and then I can, and then the other thing I need to figure out is the wavelength. Now, I'm not given the wavelength, I'm given the frequency, because it's the unit is hertz here. So that's talking about frequency, 214 hertz frequency, and I'm given the speed of the wave. Now, I seem to remember that there's something that relates the speed of the wave to the frequency and the wavelength. I don't know if you remember that one. Right? Do you remember this story here that says that the speed of the wave of any wave is always equal to the frequency times the wavelength? So that means if I want to know the wavelength, divide both sides by the frequency. So that would be the speed of the wave divided by the frequency. The wave here is sound, so its speed would be 343 meters per second, right? Because this is a speaker, so it's producing sound, and I'm given the speed of sound. So this would be the speed of the wave. And then that's divided by the frequency, which is 214 hertz. So that is 1. Let me pause for a second and calculate this. I think 1.9 maybe. Hey Siri, help me out. 343 divided by 214. 1.6. 1.6 meters. So that's the wavelength. You know, about I don't know, maybe 5'5" or something like that. Anyways, and so that's the wavelength. So then I can substitute in the story up here. I could say that the length AC is 4 meters. The length BC is 2.4 meters. And the wavelength is 1.6 meters. So this happens to be 1.6 divided by 1.6, so it gives me exactly 1. So because the ratio of the path difference divided by the wavelength is exactly 1, so that means that I get constructive interference. Right? Constructive interference, which means that I get loud sound.